Do you know what our planet's history really hides? Are you ready to face Earth's darkest, most buried secrets? Imagine that our world's 4.6 billion years of existence were condensed into a single year. Each month would represent more than 380 million years, each day more than 12 million years. A year in which every second brings upheavals, cataclysms, and revolutions. Dear traveler, welcome. We're off to explore the darkest and most troubling periods in our planet's history. From chaotic, hellish origins, to the great upheavals that almost wiped out all life on Earth, to the appearance of the most terrifying creatures our world has ever born. Get ready to plunge into the abyss of time, to discover the events that shaped our world as we know it today. But before you set off on your next adventure, be sure to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! Let's look at the sky. You see those thousands of stars. When you admire all those magical lights of the universe, it's a bit like going back in time. It's not always easy to grasp in its entirety, especially when you want to go back to the very origins of everything. Too extensive, too distant, too vague. The concept of large numbers doesn't allow us to take a concrete look at the unfolding of Earth's history. Let's reduce the history of our planet to 1 year. Just imagine, in a single second, 140 years pass before your eyes. 1 minute, over 8,300 years in the blink of an eye. An hour, and we're propelled through 500,000 years of history. Each passing day represents a dizzying leap of nearly 12.5 million years. If we consider that the Earth is completing its first year today, then the Big Bang, which took place some 2 years before the Earth was formed, would be 3 years earlier than today. After the Big Bang, particles come together to form the first atoms. The notion of space and time appeared, as did matter and light. The formation of gas clouds and gravity give rise to the first galaxies, stars, and planets. This is what gave rise to our solar system. The explosion of a nebula created a gigantic cloud of gas and dust. With gravity, this cloud became denser and eventually collapsed in on itself. In the center, the beginnings of the Sun, our star. 19 hours before the birth of the Earth, the Sun is born. Around it gravitates celestial dust. After a few thousand years, or a few minutes on our scale, this dust agglomerates, sticking together to form the telluric planets. Further out, the gas in the cloud will form gaseous planets. 4.6 billion years ago, the Earth appeared alongside the Sun. It's 000 on January 1st. It's only 19 hours since the primordial nebula collapsed in on itself. During this time, billions of dust particles have gravitated around the Sun. And then, with the help of gravity, they bonded together to form our planet, planet Earth. When it was born, our planet was unbreathable. A gaseous envelope surrounds it like a cocoon. This is the primitive atmosphere. But it contains not the slightest trace of an oxygen molecule. The planet is a gigantic molten rock, several kilometers in diameter. Earth's first days are close to what our minds might describe as chaos. The air is unbreathable. Volcanic eruptions seem to be ripping open the Earth's soil on all sides, and it's over 2,000 degrees Celsius, or 3,632 degrees Fahrenheit, on the surface. In the first days of its life, our planet doesn't evolve much. The Earth remains extremely hot, unbreathable, and hostile to all forms of life. What could possibly hatch in this desolate landscape? There is, however, one event that will take place today, January 3rd, 3 days after the birth of our planet, and which will have a considerable impact on our future life. On the scale of the Earth, this means that this event took place some 36 million years after its birth. After 3 days of life, our planet seems to have been following the same axis of rotation since its birth. But on this orbital axis around the Sun, it is not alone. Another celestial object the size of Mars orbits the Sun on the same lifeline. This object is called Theia. Until now, this cohabitation has posed no problem for either Earth or Theia. But on January 3rd, Theia left the Lagrange point, i.e. the point of gravitational equilibrium, and collided with our planet at 40,000 kilometers per hour, or 25,000 miles per hour. The impact was enormous. The force of the impact completely destroys Theia. The billions of pieces that make up Theia, along with billions of tons of rock that make up the Earth's crust, are hurled into space and into orbit. The debris from the Earth and Theia, in constant gravity around the Earth, will then gradually coalesce to form the Moon, our natural satellite. After several days, our natural satellite finally orbits us. The Moon is not the only consequence of this extraordinary impact. The Earth is becoming more massive by the minute. It is approaching the mass of our current neighboring planet, Venus. It gained in mass, but also in gravity, and managed to retain a thicker atmosphere. This celestial shock has also led to the formation of a larger core that now acts perfectly as a magnetic shield. It will protect the planet from solar particles and the winds of our star. This is one of the remote events that had to be part of the equation if life was ever to be possible. Earth will experience impacts like this, albeit on a smaller scale, throughout the first quarter of its life. For the first 3 months, it is bombarded from all sides by meteorites, asteroids, comets. Not a day goes by when it seems to be at peace with the rest of the universe. January 1st to February 11th corresponds to the Hadean Eon, a period stretching from 4.56 to 4 billion years ago. During this period, the Earth is as hot and active as ever, a veritable hell. The Hadean Eon lives up to its name. Inspired by the name of Hades, the Greek god of the underworld, we can't help but be shaken by such violence. Earth's activity is relentless and powerful. Our planet is ripped open by lava on all sides. Despite what the images suggest, however, not everything is negative. Despite this desolate panorama, perpetual volcanic outgassing is gradually helping to form the Earth's first atmosphere. It's one piece of the puzzle. Our atmosphere is one of the key elements in the history of life on Earth. It is composed mainly of gases released during the formation of our planet. These include carbon dioxide, methane, ammonia, nitrogen, and water vapor. Added to this are the gases released by erupting lava. Little by little, interactions between the atmosphere and the Earth's surface will come into play. On January 8th, 4.4 billion years ago, water vapor in the atmosphere condensed and fell as rain, forming the first ocean. It fills every hollow in the ground, forming lakes and seas in every corner of the globe. Rainfall is torrential. Between 4 and 7 meters, or between 13 and 23 feet of precipitation, 10 times tropical rainfall, falls over a period of around 100,000 years. The most diluvian rainfall does not slow down land activity and bombardments. In addition to this abundant, intense, and long-lasting rainfall, celestial bodies continue to impact the Earth. These impacts produce considerable energy. Take a look. This asteroid, tens of kilometers in diameter, will impact the Earth within 5, 4, 3, 2, 1. The liquid water that seemed to have formed the oceans just a fraction of a second ago will be vaporized by this disproportionate impact. This process will continue unabated for millions of years. The oceans vaporize, then condense and precipitate, then vaporize, condense, and precipitate again. Research into the phenomenon of ocean formation is still ongoing. Investigations into such remote periods are always as interesting as they are complex. But one thing is certain: a meteorite impact of this magnitude releases enormous energy. Its impact on climate and geology is inevitable. The Hadean chapter, which begins at the same time as the birth of the Earth, ends here, after its first few weeks of life. It represents the time interval between the Earth's formation and the first reliable rock and mineral elements in the geological record. The face of the Earth is now outlined. It is covered by oceans separating land masses called continents. As it cools, the lithosphere, made up of the crust and the rigid upper part of the mantle, solidifies. The lithosphere overlies the asthenosphere, which is solid but elastic and extensible, and therefore capable of movement. Tectonic plates move in response to the Earth's activities. In the not-too-distant future, they will be able to move apart, collide, or combine, changing the configuration of oceans and continents. It's time to tell you the second chapter of our story. It's now February 8th. The first continental landmasses, probably small and scattered, make their appearance. Volcanic activity and the accumulation of solidified matter, characterized by the Earth's cooling and continuous solidification, mark the period we call the Archean in geology. This accumulation of matter requires several tens of millions of years before we can truly speak of continents. It was shortly before March 1st that these proto-continents came into being. Of course, these masses are still much smaller and less differentiated than modern continents. These emerging lands are essentially composed of rocks. Mafic and ultramafic rocks, to be precise. That is, magmatic rock containing minerals rich in magnesium and iron. And that's about it. Water and magmatic rock, That's what our planet looks like at the end of March. We've come to the end of the first quarter of the year. The amount of time that has passed represents almost a quarter of the Earth's total lifetime. And yet, there's nothing to suggest that the slightest form of life could ever hatch here. The Earth has cooled considerably since its birth. It's true. But the Earth's crust is still very hot. Impacts keep hitting the Earth, and the oceans vaporize as quickly as they pour onto this chaotic soil. But this March 3rd will change everything. Oceans have already appeared during the Hadean, but it's here now during the Archean that ocean basins develop in a more stable way. Through precipitation and crustal solidification, it would seem that the Earth finally managed to cool down enough to establish the beginnings of a constant, stable marine environment. This tiny little drop, which fell straight from the moisture-laden sky this morning, fills this little hollow in the rock a little more. The water accumulates and accumulates. Soon a veritable pool is formed. It's a long way from being able to enjoy the song of the waves and the sweet scent of the sea spray. But look at this water. There's something reassuring about it. Since January 1st, the day the Earth was born, nothing has ever seemed as calm and soothing as the formation of this body of water. The violence of eruptions and the chaos of rock finally seem to leave a little room for this beneficial water. 24 hours have passed. While the Earth was born on January 1st, life finally appeared on March 4th. So life appeared 3.8 billion years ago, but it could be that its appearance was earlier, perhaps even during the Hadean, 4.2 billion years ago. These first forms of life are bacteria that feed on sugars present in the primordial ocean. Nearly 3 months after the birth of our planet, life evolved towards the first form of photosynthesis. On March 24th, we find a very special geological formation, stromatolites. Take another look at this stagnant water. This ocean basin is the cradle of the very first forms of microbial life. These are simple unicellular organisms, but life is here. It beats. It vibrates. These cyanobacteria thrive in shallow waters like this. They form a kind of microbial carpet. They trap and bind sediment. The result is the distinctly layered fossilized structures we'll discover a few hundredths of a second before midnight on December 31st. Over hundreds of millions of years, these cyanobacteria will modulate not only their environment, but also the Earth's very atmosphere. Yes, even now, with this tiny, simple, single-cell snippet of life, dynamic relationships between heaven and Earth are already taking shape. What's special about these living organisms is that they use photosynthesis to produce oxygen, an element previously unavailable. The first form of photosynthesis is called anoxygenic photosynthesis. Bacteria do not use water molecules as electron sources. In bacterial anoxygenic photosynthesis, oxygen is not produced as a byproduct, but rather elemental sulfur. The atmosphere was sorely lacking in free oxygen. As cyanobacteria are anaerobic beings, this environment didn't bother them in the least. They proliferated and developed as they pleased, provided the water wasn't too deep. March, April, June, bacteria evolve, and now, 3 months later, they have succeeded in using an oxygenated photosynthesis process. This time they split water molecules and release oxygen. They are the very first organisms capable of oxygenated photosynthesis. It's time to pause for a moment and take a step back. It's the beginning of June. Almost 6 months have passed. Apart from microbial life forms in the ocean, no other form of life has yet managed to settle on our planet. Seen from the sky, stretches of water and a few stretches of emerged land, resembling a rocky desert chaos, can be seen for miles. But after these 6 months, our planet is about to undergo a major biological revolution. The emergence of these 2.0 bacteria marks a new turning point in our history. Oxygen is accumulating more and more in the atmosphere. This very special event is one of the key pieces missing from our chessboard if life is to win the game and truly conquer our planet. Although the atmosphere was previously devoid of oxygen, it was laden with other elements such as methane, ammonia, water vapor, and of course carbon dioxide. But all this was without counting the appearance of cyanobacteria and their photosynthesis skills. The proliferation of bacteria promotes the production of oxygen. This oxygen then accumulates in the atmosphere, forming what is known as the ozone layer. Ozone is a gas made up of 3 oxygen atoms. Although it is a minority in the atmosphere, there are around 8 ozone molecules for every 1 million air molecules. It forms an essential protective layer in the stratosphere at around 20 kilometers or 13 miles in altitude. It absorbs ultraviolet rays, particularly UVB rays, which are harmful to living organisms. At the same time, the Earth continues to experience significant geological activity. These include plate tectonics, as well as numerous impacts with celestial bodies. Like the volcanic eruptions we mentioned earlier, these phenomena should not be seen in a negative light, despite their apparent violence. These different elements will promote the alteration of the Earth's crust. In other words, they will change the physical or chemical properties of the rocks and minerals making up the crust. Since mid-March, for example, we have seen the formation of banded iron, sedimentary rocks containing alternating layers of iron-rich minerals. It is the interaction between iron and oxygen in seawater that has made this formation possible. This phenomenon continued over the following hundreds of millions of years, and can even be said to have intensified drastically. The evolution of life is directly linked to this precise moment in our history. Higher oxygen levels encourage the development of aerobic organisms, i.e., microorganisms that need oxygen to thrive, and pave the way for the evolution of life forms. This is where it all counts. It's today that life takes on a whole new aspect. And so, on June 14th, we are no longer faced with single-celled life in its simplest form, but with a new, complex, multicellular life form, eukaryotes. The Proterozoic begins on June 14th, just a few hours after midnight. It will last a few months until around mid-November. At this point in our planet's history, climatic upheavals multiply. The planet will experience 3 major periods of intense glaciation. Shortly after celebrating the arrival of oxygen in the atmosphere, life and banded iron in the ocean, the first period of glaciation began. the Earth is now entirely covered in ice. The oceans are frozen solid, several kilometers thick. Seen from the sky, the Earth is no more than a huge snowball. On July 14th, the Earth gradually emerges from its first ice age and drops its mantle of ice. A few days later, the Earth experienced one of its first mountain formations, the Hudsonian orogeny. An orogeny is a mountain system built on an unstable portion of the Earth's crust when it underwent a major contraction. The Hudsonian orogeny is the most important mountain building event of its time. It formed what is now known as the Precambrian Canadian Shield and the North American Craton. The Canadian Shield is a zone of magmatic rock, formed through the cooling and solidification of magma or lava. It forms the origin of the geological core, so to speak, of the North American continent, Laurentia. This great orogenic belt is believed to be the largest in the Paleoproterozoic era. Later, around September 20th, a second orogeny took place, the Grenvillian orogeny. It is associated with the construction of the supercontinent of Rodinia. It is one of the two most important orogenies the Earth has ever known. The second is the Pan-African orogeny, which takes place around November 1st. This last orogeny occurs between two periods of glaciation. So, to sum up this part of our history, the Proterozoic has seen 3 periods of glaciation, 3 orogenies, but also 3 supercontinent formations: Columbia in August, Rodinia in the end of September, and Pangaea in mid-November. So it's fair to say that the last few months have been very intense in both climatic and geological terms. But at this stage in the Earth's history, there's also been a lot of movement in the living world, and it's high time for us to take a closer look. We're already almost at the end of August, with just 4 months of life left to study. While the Earth welcomed its first living organisms at the end of March, it took another 5 months for things to evolve significantly. Shortly after the first orogeny, between 2 meteorite impacts, eukaryotes underwent mitosis. In other words, eukaryotes are capable of cell division. A mother cell divides into 2 daughter cells that are genetically identical to the mother cell. This is a minor revolution in itself, but it was far from the only one. It was only a few days later, around September 1st, that scientists began talking about endosymbiosis and characteristic evolution in eukaryotic cells. If this theory is correct, then a host cell that has engulfed photosynthetic cyanobacteria will form the very first symbiotic relationship in the history of our planet. During the month of October, eukaryotes become capable of using a new multiplication process, meiosis. It took almost 4 weeks for this new phenomenon to become possible. Unlike mitosis, meiosis creates 4 gametes with distinct genetic identities. This is a giant step forward in the evolution of living organisms. Scientists have found many microfossils dating from this period. Unfortunately, they are still unclassifiable. In the end, we know very little about these subjects. Time has taken its toll, and we can't make their testimony very explicit. However, we are sure that they were eukaryotes. They were large, with a shell made of chitin, a tough, flexible organic substance that forms the cuticle of insects, and other arthropods today, and appendages of all shapes and sizes. It is thought that these microorganisms were an important part of the plankton. They share the ocean with new living beings, far removed from the first bacteria we have seen so far. The ability to create different cells opens up a much wider range of possibilities for living things, which soon adapt to their different living conditions. We are on November 13th, at the time of the appearance of the Ediacara fauna, what we might call the first animals. We can see a Namacalathus here, an animal with a calcified skeleton. It is one of the living organisms that benefited from the production of oxygen, which now accumulates in both the atmosphere and the oceans. Namacalathus is one of the rare witnesses to this period. Most of its contemporaries have soft bodies that do not fossilize. However, traces of their passage can be found in sediments, giving us a vague idea of their presence and shape, such as Sprigina, Dickinsonia, and Tribachidium. Charnia, which resembles a plant, can also be found in this oceanic land. It is shaped like a feather and lives firmly attached to the seabed. It filters the water and feeds on microorganisms more commonly known as plankton. Last but not least, we see major developments in algae, notably green algae, a group that diversifies and promotes the transition of plants from the aquatic to the terrestrial environment, but also red algae and brown algae, which contribute to the diversity of the very first marine ecosystem. The Proterozoic chapter closes with this wonderful news for the living world. In addition to major climatic, environmental, and geological changes, the Proterozoic eon lays the foundations for a future explosion of marine life. It embodies the transition from single-celled life to complex multicellular organisms. We can also see that, geologically speaking, terrestrial activity is still intense. The various orogenies and continental evolutions show us that the Earth is dynamic, in perpetual change, and that there are bound to be events arising from this vigorous internal activity. We are now approaching the end of our year. The Earth's entire life, from birth to the present day, is coming to an end. Its history is drawing to a close, yet there is still so much to discover. Today is November 17th. Only 44 days separate us from the emergence of the first multicellular animals to the present day. There will be a before November 17th and an after. This date is very special for our planet. In fact, it's one of the most significant events in our history. We've just gone through almost 10 months on Earth. These 10 months represent the Precambrian supereon, in which we find the Hadean, the first weeks of life on Earth, then the Archean, and finally the Proterozoic. Between November 17th and 21st, we're in the Cambrian period, the very first era of the Paleozoic eon. New groups of animals multiply to such an extent that scientists speak of an explosion of life. The Cambrian changed the order of life forever. The emblematic animal of the period is the trilobite. Unlike previous animals, which lacked diversity and were very simple, we can see that life evolved just by looking at this marine specimen. The invention of the shell and carapace, while facilitating fossilization, and thus enabling us to find these precious witnesses to the past, was above all a major development in marine diversification at the time. At last, we can start talking about ecosystems and biotopes. The seabed is home to numerous arthropods, including trilobites. Crustaceans and chelicerates can be seen here and there, as well as members of the mollusk family, such as gastropods and a few brachiopods. We're still a long way from the seascape we know, but it's amazing how much life seems to abound. We can see Opabinia, Branchiacaris, and even Achaea. The latter looks a bit like a small marine centipede. It's easy to find its way around the seabed, which is teeming with life. We can also observe some very strange creatures, such as this Pangaea, a possible ancestor of vertebrates, Canidaspis, but also Hallucigenia, with a very peculiar silhouette. A little further on, we find another trilobite, the trilobite Olenoides. He, like this Wuaxia and all the others, should beware of this approaching Anomalocaris. As in any ecosystem, a predator-prey relationship is established. The very first true ecosystem on Earth is no exception to this rule of nature. While many of the animals we have mentioned are suspension feeders or filter feeders, Anomalocaris is the very first predator in the history of life. Its evolution is remarkable. It has compound eyes like flies and 16,000 facets. It also has a mouth, teeth, legs, fins, and even a long tail. It's a far cry from the single-celled being or basic microorganism we encountered before the Cambrian period. Here we see the emergence of specific organs with a specific role. The evolution and diversification of living organisms is underway. While in the ocean, everything seems possible from now on. On the surface, it's a different kettle of fish. Here, the landscape is quite different. A sorry sight, isn't it? On land, everything seems to be limited to rock and dust. It has to be said that although the ozone layer is thickening, it is still too thin to truly protect the surface of the continents. Without this protection, ultraviolet rays easily destroy the little life that might have the courage to settle. There's not the slightest plant cover for miles around. Without this protective green carpet, the continents are in a bad way. Erosion is intense. On the continent of Gondwana, you can see how arid and desert-like the region is. We're entering a new era. During these 4 short days, the Earth will experience intense activity. While the northern hemisphere is totally devoid of landmass, the southern hemisphere is home to the impressive continent of Gondwana, which includes South America, Africa, India, and even Australia and Antarctica. A little further away in the tropics, we can also see 3 other continents. Laurentia is already there, but so are Siberia and Baltica. These continental masses are not static. They move and change the order of things. Hour by hour, they trigger the opening of the Reek Ocean to the south, or the beginning of the closing of the Lapitous Ocean. This plate movement undoubtedly includes phenomena that have a major impact on living organisms. The activity of the Reek Ocean Ridge, for example, causes the oceans to overflow onto the continental shelves. Minute by minute, the level rises. It is now 200 meters higher than today. Perhaps this is what enables plants, like Marchantia polymorpha, to land on Earth. Until now, life has been exclusively marine. We're still a long way from a rich and diverse biotope on the continent, but the arrival of this liverwort plant on the soil gives us great hope for the future. Back to the ocean, during this short 4-day period at the end of November, life had time to regain its strength and diversify once again. On November 24th, a wealth of marine life can be seen blooming all over the globe. Right in front of you, in this part of the ocean, is a Treptoceras, an orthoceran cephalopod mollusk that is very common in the rocks of the Cincinnati region, a region that is currently in the United States. At 30 centimeters or 12 inches, this orthoceran is far less impressive than one of its relatives, Chimeroceras, which would reach 10 meters or 33 feet in length. If the Cambrian is associated with a trilobite, the animal that epitomizes the Ordovician is rightly the orthoceran. In the large predator category, we can also mention Megalograptus, a eurypterid also known as a sea scorpion, measuring around 80 centimeters or 30 inches long. It attacks a trilobite, probably an Isoletus. The latter are in increasing decline. Other animal groups, on the other hand, are diversifying and expanding. Here, members of the conodonts, Promissum, and a few meters away, Manitolinoceras, a nautiloid cephalopod. It takes full advantage of the resources and shelter provided by these Brachiospongia sponges, solitary corals that resemble sea anemones, bryozoans that look like colorful little bonsai, and Olicera, stromatoporids, that are also enriching the construction of the first reefs. The richness of marine biodiversity has developed impressively. The number of families has tripled, and the number of genera has quadrupled, according to data detailed by Sepkoski, an American paleobiologist. Speaking of this eminent scientist, the database that bears his name represents a compilation of data on over 30,000 fossils and remains a benchmark for the study of paleobiodiversity worldwide. Let's return to the geological and climatic conditions of our marine animals. The drop in surface water temperature may have favored this marine richness. We've gone from 45 degrees Celsius to 30 degrees Celsius, or from 113 degrees Fahrenheit to 86 degrees Fahrenheit, an enormous difference that inevitably impacts aquatic life. Phytoplankton and bottom-dwelling algae are the first to benefit from this windfall. Animals dependent on these first organisms also benefit by extension. As a domino effect, the multiplication of the base of the food chain has enabled filter feeders, grazers, and other so-called primary consumers to develop and diversify. Of course, predators are not to be outdone. On land, although everything is still very fragile, an incredible event is taking place: the conquest of the continent by living organisms. For the time being, it's just a little moss that settles on the water's edge. This time on land, it's not just rocks, sediments, and minerals, but life that's beating a path. Marchantia polymorpha was one of the first plants to settle on the ground and anchor itself in the soil, along with a few mosses and bryophytes. the expansion of terrestrial plants was accompanied by an acceleration in the chemical erosion of volcanic rocks on the continents, which reduced the concentration of CO2 in the atmosphere. The weathering of continental rocks also releases large quantities of phosphorus, which is transported by rivers to the oceans. What does this mean for marine fauna? Everything. This enrichment has favored the development of phytoplankton, increased photosynthesis, and enabled a multitude of species to develop and diversify. This new nutrient source has enriched the biotype, enabling the development of new ecological niches. If all seemed well and good for marine fauna and flora, and all seemed possible for terrestrial beings, that was without taking into account the first catastrophe to take shape on November 24th. For several minutes now, an ice age has been brewing. It will soon wipe out a quarter of all marine animal families and half of all marine animal genera. It's the second biggest extinction on Earth after the Permian. Increased photosynthesis is at the root of atmospheric CO2 depletion. This is undoubtedly what ultimately triggered the famous glaciation responsible for the biological crisis that followed. For the first time, life has to recover from a biological crisis on a massive scale. Nature will have to get used to this renewal, and it won't be the last one it experiences. November 25th, we enter the Silurian period. With it, flora and fauna must once again blossom. It will take a few hours to achieve this, thousands of years in fact, but the Earth has many resources of its own and does not give in so easily. The generalized warm climate allows coral reefs, populated by tetracoralliariids and tabulates, to take over the edges of the Panthalassa and Paleotethys on the shallow seabed. The melting of the polar ice caps is causing a general rise in sea levels, and shallow seas are now covering continental shelves. Speaking of continental shelves, there's a major geological event to note. Do you notice these mountains? They're a sign of the slow formation of the Caledonian orogeny. Let's dive back into the ocean and see how life returns to normal. Eurypterids reign supreme during the Silurian. Here, it's an acutoramus. It can reach 2.5 meters or 8 feet. The Silurian also saw the emergence of new groups. A few days ago, during the Ordovician, agnathans or jawless fish appeared. But it was only a few days later, during the Silurian, that they experienced a real evolutionary bonanza. The group now includes anaspids, heterostracans, osteostracans, and telodonts. A few minutes later, gnathostomes, the jawed vertebrates, appear. A new evolutionary turning point for fish. Acanthodian Climatius reticulatus, one of the very first jawed vertebrates on our planet, crisscrossed the world's waters. Other fish even display their first mobile scales. Not far away, we can see Eurypterids attacking an emblematic predator of the previous period, the giant Orthoceron, and dethroning it from its position as alpha predator. But in a few hours' time, he'll be up against something much stronger. Placoderms, or armored fish, dominate Silurian ecosystems. Giant forms, like Dunkleosteus, are fearsome predators that are going to take Eurypterids by storm, even the biggest of them. life is booming for many other groups of marine animals, including echinoderms, mollusks, and graptolites. If the changes are significant in the water, it's at the surface that they're most impressive. Up until now, the Earth, impoverished by erosion and ultraviolet rays, had left only a barren, arid, almost chaotic landscape on which no plants had managed to take root. But on November 26th, everything looked different on Earth. Hope is there at the water's edge. Not only algae, but also vascular plants have emerged from the water. Life is gradually returning to the continent. It is through Cooksonia that the first river and seaside vegetation is taking root. The arrival of this plant led to the creation of a small ecosystem. It's still in its infancy and fragile, but it's promising. From second to second, it grows, develops, and takes on real meaning. Take a good look at the ground. An inhabitant has already found a home in this little corner of the vegetation. You can see the first scorpion capable of taking a few steps on land, Paleophonus. But there are also spiders and terrestrial myriapods like this millipede, Pneumodesmus. One of the most interesting features of its skeleton is the presence of stigmata, i.e., tracheal openings. It was one of the very first living creatures to walk the Earth. Until now, almost no other creature was capable of doing so. In water, lift is different. Here you have to support your own weight and air pressure, breathe differently, and move without the help of the water. The animals you've just seen are the first to achieve this feat. On Earth, an end is always a sign of a beginning. In the space of a few hours, a few days at most, drastic changes take place, and new processes are set in motion. In geological terms, the Devonian period saw the end of the Caledonian orogeny, but also the beginning of the Hercynian orogeny. For animals, the few hours separating November 28th and December 1st marked the end of their lives. Osteostracans, placoderms, pelagic graptolites, and anapsids gradually disappeared during this period. Ecological niches were left vacant, allowing other species to fill the void. New groups appear. A few hours later, groups such as lungfish, the impressive holocephalans, elasmobranchs, osteolepiforms, and coelacanths made their entry into the aquatic world. The marine world is a little more active than a few days ago. The animals are quite different from those we've encountered so far. Large hunting animals are making their appearance, such as this Dunkleosteus, which is attacking a shark, a Cladocelicae. Other predators are more modest in size, such as Cherolepis, which attack schools of acanthodians. Among fish, we see significant radiation. Actinopterygian, osteichthyans, or ray-finned fish, like this, Cherolepis, are increasingly populating the world's oceans. Another important group is also making its mark on the seabed. The Sarcopterygian, osteichthyans, or fleshy-finned fish, are appearing alongside chondrichthyans, such as the primitive shark, Cladocelicae. The ocean's architects continue to build masterpieces, such as stromatoporoids, tabulate corals, and tetracoralliar corals. Coral reefs are enriched and developed, and are home to hundreds of different species, like these few brachiopods and goniatites, coiled cephalopod mollusks. On land, the landscape has never been so peaceful and reassuring. Vegetation, albeit small, most of it around 10 centimeters or 4 inches, is covering more and more of the surface. A real vegetation cover is beginning to take shape. If you're observant, you'll see that in a few places, one plant is a little taller than the others. It's also a more intense green. It's a lycopod, Asteroxylon mackay. It measures around 50 centimeters or 20 inches. But it's not the only one. Let's take our investigations a little further afield and head for the Appalachian Mountains. Here, the temperature is around 28 degrees and humidity is very high. This is one of the oldest forests in the world. It's extraordinary to finally see such a landscape taking shape before our eyes. Like today, it operates in stages. At the water's edge, you can see the smallest plants, such as lycopod Leclerquia. Then, a little further on, some sort of bushy, scaly bushes, the Radinia. Then, Tetraxylopterus along the edge of the young forest. There are herbaceous lycopods, but above all, tree lycopods. These are the very first trees in the world. The tallest are undoubtedly the Euspermatopterus, 8 meters or 26 feet approximately. They look a little like palm trees. It's hardly surprising that new ecological niches are opening up with the advent of such extensive plant cover. Collembola, like Rhyniella precursor, occupy the area, but also and above all the first tetrapods. It's now December 1st, 1 a.m., and we're witnessing the birth of Tiktaalik, the first aquatic tetrapod. A few hours later, at around 8 p.m., one of the oldest tetrapods, the famous Ichthyostega, also appeared on our beautiful blue planet. It preserves the characteristics of a fish, with a caudal fin, tail, and ventral face covered with small scales, but also the first true tetrapod limbs with 3 joints, hip, knee, and ankle. The reason it's so famous is undoubtedly that it was one of the very first aquatic vertebrates to attempt an adventure on the continent. It is both adapted to swimming and to locomotion on land. Despite this good news for terrestrial life, no doubt caused by the depletion of oxygen in the oceans, a new mass extinction is raging on our planet, causing the loss of almost 75% of species. December 2nd. We are now entering a new period, the Carboniferous. The collision of the European, American, and Gondwanan plates continue the formation of the Hercynian chain and welded almost all the continental masses into a single supercontinent, Pangaea. In just a few hours, the intense erosion that accompanied the formation of the Hercynian chain, coupled with the lush vegetation of the coal forest, continued to drive down the amount of CO2 in the atmosphere, and consequently, the planet's temperature. The land masses of the South Pole are covered with ice. Are we facing a new biological crisis? For now, let's return to December 2nd. In the space of a few hours, the huge variation in temperature between the poles and the equator causes a zonation of vegetation. The equatorial zones are covered by large coal forests, with lepidodendrons, sigillaria, calamites, and chorditas. In temperate zones, deciduous trees such as Glossopteris gradually take over. In swamps, a wide variety of other plants also provide new ecological niches. Neuropterus, for example, can be seen in the explosion of seed plants. As reproduction becomes easier, the development of these plants extends over an ever wider territory. Vegetation cover became more diversified and denser. This great diversification of vegetation encourages the expansion of a diverse and luxuriant terrestrial fauna. On December 3rd, amphibians such as actinodon took up residence in the marshes. Insects are also abundant. There are centipedes, spiders, scorpions, but also the first flying insects, such as Stenodictia, or a giant version of the dragonfly, such as Meganeura. Other giant versions of insects will appear in early December, alongside this dragonfly, with a wingspan of almost 70 centimeters or 28 inches. Arthropleura is a centipede measuring 1.5 meters or 5 feet long. It's gigantic time. According to scientists, there is an explanation for these disproportionate sizes found in many insects of the time: high oxygen levels. Indeed, during the Carboniferous era, a particular event favored this significant increase. The Carboniferous era takes its name from the formation of coal. The great trees we have seen would lead, as they collapsed into wet spoils, to carbon deposits that would become our main coal reserves many weeks later. But for the time being, as the carbon is buried in the soil, the oxygen level in the atmosphere increases, 15 to 25% more than at present. Insects are benefiting from this influx of oxygen, to say the least. Another major event is the arrival of the amniotic egg. If this is a new impetus for the emergence of new species, it's not the only one of the period. On December 5th, synapsids appear. A few minutes later, they diversify, adding new groups and species. The sauropsids soon follow suit. By midday on December 6th, the two great clades of synapsids and sauropsids were already perfectly established. Hylonomus, one of the first sauropsids. A few seconds later, Petralicosaurus also appears, the oldest known diapsid that will undoubtedly give rise to the great clades we all know: crocodiles, dinosaurs, but also the birds from which they are descended. We can also see Archaeothyrus, the oldest synapsid that gave rise to the mammalian lineage. The Permian puts an end to the Carboniferous with the end of the coal formation so characteristic of the period. In fact, during this new period of just a few days, a fungus appeared that made all the difference. It was capable of degrading wood, or at least the lignin of which it was composed. It thus puts an end to the formation of charcoal. While this fungus marks a real split between the two eras, there are also certain continuities. Pangaea, for example, has now reached almost its climax. The continents of Gondwana and Laurasia seem virtually unified. The synapsids we met just a few hours ago are now the main dominants of their ecosystems, as in the case of the carnivorous Lycanops of the Gorgonopsian family. Amphibians, despite their dominant role in previous eras as the first vertebrates to embark on a partly terrestrial life, are increasingly giving way to these synapsids, but also to the anapsids, the periosaurs. Periosaurians were large anapsid reptiles adapted to life in swamps, like today's hippopotamuses. Their limbs are stocky and erect, and their bodies are covered with dermal armor. They are herbivores up to 3 meters or 10 feet long. Until now, no land animal had really adopted this diet, but little by little, synapsids welcome their first vegetarian. The first bipedal animals appear. This mode of movement enabled them to gain in agility or speed. Others try to fly, or at least glide at first. However, there is no shortage of predators down there. We've seen that Lycanops are fierce predators, but they're far from the only ones. A few archosaurians make a timid appearance, but synapsids remain by far the dominant vertebrates of the period. Trees are still very much in evidence, some of them very large and offering excellent ecological niches where insects and small reptiles abound. Other genera, such as cycads, a palm-like plant, enrich the biotype of Permian forests. In spite of all this radiation, a major biological crisis hits the Earth. Up until now, life seemed to be well underway and running its course. One evolution followed another. Major radiation processes were taking place, and marine and terrestrial ecosystems were flourishing. But on December 11th, intense activity and brutal events upset the established order. For more than 1 hour, i.e. almost 500,000 years, one volcanic eruption followed another. They form a layer of lava 6 kilometers thick. Just imagine, 6 kilometers or 4 miles thick. The amount of gas produced is just as phenomenal. Temperatures soar to over 40 degrees Celsius or 104 degrees Fahrenheit, while oxygen levels plummet. 75% of terrestrial species and 95% of marine species will eventually disappear. It is sometimes described as the mother of all extinctions. The Earth has already experienced its 4th extinction, but this one is undoubtedly the most severe and intense of all. 95% of species have been wiped off the map. The cycle of life seems annihilated. Asteroid impacts and intense volcanic activity appear to be the cause of this exceptional biological crisis. The Permian, like the Paleozoic supereon, thus closes on this tragic note, yet another major biological crisis. But like any period of crisis, a new diversification follows, with the birth of new species and significant evolutionary radiation. In short, life begins again. During the Paleozoic, periods follow one another in rapid succession. As we have seen, they are shorter and more intense. An era lasts just a few days, yet geologically, climatically, and biologically, the changes are enormous. But from the Mesozoic onwards, everything seems to accelerate even further. The pace is intense. Radiation and biological evolutions multiply. Everything seems to be in turmoil, without ever running out of steam. December 11th. In the aftermath of a major biological crisis, flora and fauna regain a certain vitality. Life returns, but not for long. The Triassic is the only period in our history to begin and end with a mass biological crisis. It takes a few minutes for the Earth to catch its breath. On the whole, plants survived the crisis rather well. The lycopodiales and cycadales we've just seen, but also ginkgophytes and the famous Glossopteris are still present. Such flora undoubtedly facilitated the return and diversification of the fauna. Little by little, the vegetation of the northern hemisphere took on a new look, with conifers becoming more numerous and diversified, like these yuccites. Among animals, too, we can see that some are being stripped of their rank, and others are stepping in to fill the gap. Until now, amphibians have occupied a large space, and synapsids have been fairly well established, but diapsid reptiles are gradually conquering the continent. It has to be said that the famous archosaurians, which had been very shy and few in number in previous eras, are taking full advantage of the biological crisis to fill the vacant ecological niches. A few minutes after the stroke of midnight on December 12th, they took advantage of an exceptional radiation. They would later give rise to several lineages, including crocodiles, dinosaurs, and pterosaurs. During the Triassic period, crocodilomorphs such as Saurosuchus and dinosauromorphs such as Lagarpaton, Salosaurus, and Marasuchus were the main competitors for land. A few seconds before the end of the Triassic period, the very first dinosaurs appeared, such as Procompsognathus, which despite its small size, was the origin of the terrible T-Rex. It feeds on insects, lizards, and other small prey. It may also have scavenging tendencies. You may also come across a Plateosaurus. Don't worry, it's a vegetarian. A few amphibians will survive the crisis. The Stenatosaurus, for example, which enjoys a bit of peace and quiet in this swamp, is one of the labyrinthodont amphibians. A few amphibians that survived gave rise to the lineages we know so well today, notably frogs and salamanders. In the oceans, nothosaurs roam the seas in search of food. They have a voracious appetite. Alongside them, other groups are emerging, but they remain very discreet for the moment. No doubt they're biding their time, waiting to show what they're capable of. Here we see one of the first turtles, and probably the very first mammal on our planet. On December 15th, a new crisis struck our blue planet. We don't really know what caused the extinction. Could it have been the massive eruptions at the time of the breakup of Pangaea? These would undoubtedly have resulted in the production of large quantities of carbon dioxide, which would undoubtedly have had an impact on the climate. Perhaps asteroids also hit the Earth? The Manicouagan crater in Canada and the Chassenon-Rochechouart crater in France bear witness to such impacts. What we do know, however, is that 70 to 80% of species disappear. During the Jurassic period, dinosaurs experienced an exceptional radiation. They took advantage of the aftermath of the crisis to fully conquer the territories they coveted. They adapted to their environment, filling vacant ecological niches and becoming increasingly diversified. It's a veritable demographic explosion. Two major clades were formed. The Ornithischian clade, mainly herbivores that moved in herds, already had several members in the Jurassic. Depending on the environment or biotope, thyreophores, such as Stegosaurus, Nodosaurus, an ankylosaurus could be seen. And although they're well known, they're not the only ones. During those same hours spent living between December 15th and 18th, there are also many ornithopods sharing the same territory with the iguanodon. Or marginocephalans, including this Psittacosaurus. The second clade, as you might expect, is that of the Saurischians. They comprise two groups: the theropods, mostly bipedal carnivores, and the sauropods, generally large quadrupedal herbivores. A few specimens are known from this clade, notably Allosaurus. There's also Megalosaurus at 7 meters or 23 feet long, and the famous Archaeopteryx. This one is much smaller, but just as exceptional and important in our history. This little animal is undoubtedly the link between dinosaurs and birds. The Jurassic was also the age of giants. The nonchalant Diplodocus, which must have weighed in at around 15 tons and probably measured no less than 25 meters, or 82 feet in length, can be seen strolling along. But there's also the Brachiosaurus, which has nothing to envy it, given that one of its vertebrae alone is already 70 centimeters or 28 inches long. In fact, it reaches 12 meters or 40 feet in height, and around twice that in length. While the Jurassic period was ruled by the dinosaurs, the Cretaceous still reigns with an iron fist. Before going back to the masters of the land, let's talk about their environment. The landscape changes somewhat in the Cretaceous, and for good reason. The first angiosperms, i.e. the first flowering plants, can be seen. Insects had already evolved and diversified considerably, with the appearance of flies in the Jurassic, for example, but in the Cretaceous things move very quickly. Pollen and nectar from flowers are not yet coveted by anyone. It's a godsend. Bees and butterflies have a field day. Melitospex burmensis, the possible ancestor of modern bees, is the little insect that takes an interest in Archifructus and Montesecchia vidali, two aquatic angiosperm plants. It's now December 22nd, and the young Alps mountain range is about to change the landscape of this part of the continent too. For some minutes now, certain groups have been evolving. New species are emerging, and some of them are very popular with the general public, like the Triceratops, for example, 7 meters or 23 feet long, and 8 tons of fat and muscle. Apparently, he wasn't very good-natured. Fights had to be violent enough to win the hearts of females, but he was far from the most impressive in terms of weight. The trophy for champion in this category undoubtedly goes to Argentinosaurus. New dinosaur skills emerge in the early hours of dawn on December 24th. Feathers. Although feathers were undoubtedly present in the Jurassic, they are a much more common feature of the Cretaceous, as in Microraptor and Similicodipteryx. It's December 25th, Christmas Day, life is about to receive a very strange gift. The age of reptiles is about to come to a tragic end, with major eruptions, but also the fall of a large asteroid that will crash into Chicxulub. The crater measures 180 kilometers or 112 miles in diameter. Imagine the power of the impact. Plunged into darkness, tested by dust, gas, and acid rain, life quickly suffocates. Ongoing volcanic eruptions exacerbate the situation. For several seconds, animals fell one by one. On December 26th, they all disappeared. Only the mammals, which had kept a low profile until then, will take advantage of the space left empty by the dinosaurs to develop and diversify. Now it's time for the very last era of our planet. It's a little confusing to think that this is the period we know best, the one when the genus Homo sapiens appeared, and yet, there are only a few days left before the end of our year on Earth. We are insignificant compared to the length of its history. Mammals gradually settled on all continents and diversified widely. Some, like the marsupials, were restricted to a specific geographic zone, mainly due to plate movements that confined them to the oceanic continent. In the early hours of the morning, around 6 a.m., the first primate appears. It was Darwinius massillae. This one will be christened Ida. It's a lemur. According to the scientists who had the chance to study its skeleton, it is our oldest common ancestor. It led to the lemur, of course, but also to apes in a more global sense, and to man. You can see his opposable thumb very clearly. It feeds on seeds, leaves, and fruit. A few hours later, at around 10 a.m., India separated from the African continent and collided with the Eurasian plate. This collision follows the closure of the Tethys Ocean, which has completely disappeared in the subduction zone bordering the Eurasian continent. The Indian continental crust, which is lighter than the oceanic crust, will not subduct, but will instead indent into the Eurasian continental crust. Our greatest mountain range, the Himalayas, was born. At the same time, many new animal species will appear. All the groups we know today gradually emerge. The continents increasingly took on the shape we know today. Seasons mark the rhythm of the Earth's changing landscapes. Around 8 a.m. on December 31st, the first hominids are finally encountered. Only a few hours later, at around 11:50 p.m., a large-scale volcanic eruption at Toba in Indonesia sent ash and dust into the atmosphere. Lasting less than 1 second, a few decades on our scale, this volcanic winter caused the loss of almost 60,000 individuals of the Homo genus. It's now 11:56 p.m., and Cro-Magnon man, our closest relative, is finally present on Earth. But there are only 4 minutes left to place him on our calendar. At 2357, ice ages and interglacial periods follow one another. Despite the harsh climate, many species manage to survive. This is not the case for the mammoth, which dies out at just 2358, but man is proliferating. We're now talking about modern man. It's now 11:59 p.m., a few seconds past. We're in the Sahara. You may not remember it, but this land was once green and even humid. Many animals, including humans, took full advantage of what nature had to offer here in the way of resources. But now it's becoming dry and arid. Conditions were too difficult to survive in such an environment. Migrating to the Nile Valley, they laid the foundations of what was to become Egyptian civilization. We've only been here since 4 p.m., but Cro-Magnon man has been here for 4 minutes, and one of the oldest ancient civilizations arrived only 27 seconds ago. We're just a few seconds away from today. It's impossible to go into more detail about our history, that of mankind, but also that of fauna, flora, and the Earth in general. If we were in the infinitely large, here we are paradoxically in the infinitely small. In the end, whether we talk about our history in terms of large numbers or on a smaller scale, the scale of time remains dizzying. The Earth's history is also what makes it such an exceptional planet. Seen from the sky in a million years' time, the Earth won't change that much. Sure, the continents will move, but no more than 45 to 60 kilometers or 30 miles from their current locations. The sun will continue to shine, rising every 24 hours, and the moon will orbit the Earth in about a month. But some things will change quite fundamentally. In many parts of the world, irreversible geological processes are transforming the landscape. The vulnerable contours of ocean coasts will change particularly markedly. An active submarine volcano off the southeast coast of the largest of the Hawaiian Islands has already risen above 3,000 meters or 10,000 feet from the ocean floor and is growing every year. In a million years, a new island will rise from the ocean waves, already named Lohi. At the same time, the extinct volcanic islands to the northwest, including Maui, Oahu, and Kauai, will shrink under the influence of wind and ocean waves respectively. With regard to waves, those studying rocks for future changes conclude that the most active factor in changing the Earth's geography will be the advance and retreat of the ocean. A change in the rate of rift volcanism will take a very, very long time to affect this geography, depending on the amount of lava more or less solidified on the ocean floor. Sea level can fall significantly during lulls in volcanic activity, when the rocks at the bottom cool and settle. Scientists believe this is what caused the sharp drop in sea level just before the Mesozoic extinction. The presence or absence of large inland seas such as the Mediterranean, as well as the reunion and breakup of continents, led to major changes in the size of coastal shelf areas. To imagine the world a few 100 million years from now, we need to look to the past for clues to understanding the future. Global tectonic processes will continue to play an important role in changing the face of the planet. Today, continents are separated from one another. Vast oceans separate America, Eurasia, Africa, Australia, and Antarctica. But these immense expanses of land are in constant motion, and their speed is around 2 to 5 centimeters or 2 inches per year, i.e., around 1,500 kilometers or 930 miles in 60 million years. we can establish fairly precise vectors of this movement for each continent by studying the age of the basalts on the ocean floor. Basalt near mid-ocean ridges is quite young, no more than a few million years old. By contrast, the age of basalt near continental margins and subduction zones can reach over 200 million years. It's easy to take into account all these age data on the composition of the ocean floor to rewind the tape of global tectonics over time and to get an idea of the geographical mobility of the terrestrial continents over the last 200 million years. Based on this information, it is also possible to project the movement of continental plates 100 million years in advance. Given the current trajectories of this movement across the planet, it appears that all continents are heading for the next collision. In 250 million years, most of the Earth's landmass will once again become a giant supercontinent. Nevertheless, the exact structure of the future supercontinent remains the subject of scientific controversy. It is possible to take into account the current movements of the continents and predict their trajectory over the next 10 to 20 million years. The Atlantic Ocean will expand by several hundred kilometers or miles, while the Pacific Ocean will shrink by around the same distance. Australia will move north towards South Asia, and Antarctica will move slightly away from the South Pole towards South Asia. Africa will move slowly northwards across the Mediterranean Sea. In a few tens of millions of years, Africa will collide with southern Europe, closing the Mediterranean Sea and erecting a Himalayan-sized mountain range at the site of the collision. So the map of the world in 20 million years' time will look a little familiar. When modeling a map of the world 100 million years from now, most researchers identify common geographic features. For example, agreeing that the Atlantic Ocean will exceed the size of the Pacific Ocean and become the largest water basin on Earth. According to the extraversion theory, the Atlantic Ocean will continue to open up, and the Americas will eventually collide with Asia, Australia, and Antarctica. In the final stages of this supercontinent assembly, North America will close the Pacific Ocean to the east and collide with Japan, and South America will wind clockwise from the southeast, joining the equatorial part of Antarctica. All these parts are astonishingly combined with each other. Thus, the new supercontinent will be a single continent, stretching from east to west along the equator. The extraversion model mainly maintains that the large convection cells in the mantle, located beneath the tectonic plates, will remain unchanged in their current form. In contrast, the alternative approach, known as introversion, takes the opposite stance, referring to past cycles of closure and opening of the Atlantic Ocean. Today, both supercontinent theories, extraversion and introversion, remain popular. Whatever the outcome of this discussion, everyone agrees that while in 250 million years the Earth's geography will change significantly, it will still reflect the past. According to some simulations, in around 200 million years' time, average temperatures on Earth should fall slightly, below 12 degrees Celsius or 53 degrees Fahrenheit. At the same time, global sea levels will fall by around 200 meters or 650 feet. In this configuration, conditions for the development of complex life will remain quite favorable at low and mid-latitudes. Only after around 400 million years will average surface temperatures fall to around 10 degrees Celsius or 50 degrees Fahrenheit, and ocean levels drop by more than 500 meters or 1,640 feet from their current position. In this situation, all continents from north to south, even at moderate latitudes, will be covered by glaciers, and mountainous regions at equatorial latitudes will also be frozen. However, this cold snap will not be permanent. After a further 200 to 300 million years or so, an equilibrium should be established between the decrease in temperature due to the bacterial elimination of nitrogen from the atmosphere and the increase in the sun's luminosity. The temporary assembly of continents around the equator will mitigate the impact of ice ages and moderate changes in sea level. Where continents collide, mountain ranges will rise, climate and vegetation will change, and oxygen and carbon dioxide levels in the atmosphere will fluctuate. These changes will be repeated throughout Earth's history. A gamma-ray burst, or huge supernova, occurs less than 6,500 light-years from Earth, within 500 to 600 million years. Gamma-ray bursts are enigmatic phenomena that appear to be the most intense and energetic explosions in the universe, and astronomers assume that they are linked to extremely powerful supernovae. Fortunately, we have yet to observe a gamma-ray burst close enough to us to fully understand what is happening. So far, gamma-ray bursts have only been detected in other galaxies. But if such an event were to occur close to home on a cosmological scale, as it will in around 500 million years' time, less than 6,500 light-years from Earth, it could lead to a mass extinction. A gamma-ray burst directed in our direction, lasting just 10 seconds, could destroy at least half of the Earth's ozone layer. Large-scale ozone depletion could have devastating consequences on food chains, leading to the death of many species. A gamma-ray burst would annihilate life forms on the Earth's surface and in the upper layers of the ocean, which currently supply significant quantities of oxygen to our atmosphere. It turns out that gamma rays also decompose the oxygen and nitrogen present in the atmosphere. These gases would be transformed into nitrogen dioxide, better known as smog. This would envelop the sun over heavily polluted areas. If this smog were to cover the entire Earth, it would block out sunlight and trigger a global ice age. Due to tidal forces, the Moon has moved more than 20,000 kilometers or 12,000 miles away from the Earth. Even in the most favorable cases, the lunar disk can no longer completely cover that of the Sun. In 600 million years' time, all eclipses will be annular. The fate of the Earth is intimately linked to that of the Sun, which, like other stars, cannot shine forever. 50 million years after the Sun's formation, our star became a main sequence star. Since then, its luminosity has increased in an almost linear fashion, rising by around 1% every 110 million years. Within 600 million years, our Sun will undergo a gradual transformation, resulting in a progressive increase in both brightness and heat. This increase in the Sun's luminosity will have a significant impact on our planet, resulting in more solar radiation reaching the Earth. This increase will have an impact on the silicate minerals present on the planet, leading to increased weathering of these minerals. This, in turn, will affect the carbonate-silicate cycle, which is a geochemical process involving the interaction between carbonate and silicate. Increased weathering of surface rocks traps carbon dioxide in the soil in the form of carbonate. As water evaporates from the Earth's surface, rocks harden, leading to a slowdown in plate tectonics, which eventually comes to a halt when the oceans completely evaporate. With less volcanism to recycle carbon into the Earth's atmosphere, carbon dioxide levels begin to fall. For hundreds of millions of years now, the Earth has been experiencing a period of intense cold, with an average surface temperature of around 10 degrees Celsius or 50 degrees Fahrenheit. But now, the sun's increasing brightness is triggering a rise in the Earth's temperature, generating a series of problems. The first signs of trouble will appear within 600 million years, but it's only when the average temperature reaches 47 degrees Celsius or 117 degrees Fahrenheit, when solar luminosity is 10% higher than at present in 1.1 billion years' time, that the situation will become critical. From that point onwards, the Earth will begin to lose water progressively, resulting in a modification of its atmosphere and becoming a humid greenhouse due to the massive evaporation of surface water. At this point, the amount of water in the stratosphere should increase. These water molecules will be broken down by the sun's ultraviolet radiation via the process of photodissociation. As a result, hydrogen will escape from the atmosphere. The main result should be the disappearance of the oceans in around 1.1 billion years. This water vapor, raised in the stratosphere, will undergo chemical decomposition, separating into oxygen and hydrogen. This is when major changes will take place. Higher temperatures will cause the oceans to absorb more carbon dioxide, a gas essential to plant life. This absorption will reduce the amount of carbon dioxide in the atmosphere, causing an imbalance in the plant life cycle. It is estimated that the planet will be able to support highly organized life for another 600 million years from now, as current forecasts indicate that after this period, the sun's increasing brightness will have a significant impact on the biosphere. The emerging scenario is therefore worrying, as not only will the Earth progressively lose its precious water, but also gas is vital for plant development. Together, these elements threaten the delicate balance of our ecosystem. The high temperatures projected for the future would cause the oceans to absorb more carbon dioxide, which would disrupt the biological processes essential to plant life, accelerating the problems associated with water loss and the degradation of our atmosphere. We will be approaching the Earth's carbon dioxide compensation limit, a critical point at which the balance between carbon dioxide and oxygen becomes unsustainable for photosynthesis. In around 600 million years' time, carbon dioxide levels will be lower than those needed to maintain the C3 carbon fixation by photosynthesis used by trees. Some plants, using C4 carbon fixation, can survive carbon dioxide concentrations as low as 10 ppm. Currently, 99% of plants use C3 photosynthesis. Their ability to convert sunlight into energy is gradually declining, leading to a general decline in plant biomass. If atmospheric CO2 levels fall, the survival of embryophytic plants becomes difficult, as they require a minimum concentration of around 10 ppm atmospheric CO2. It is highly probable that the evolution of living organisms will enable a certain number of organisms to adapt to these conditions by using a more efficient photosynthetic carbon acquisition mechanism. When levels fall below this value, complex plants begin to die, leading to a reduction in oxygen production. This decrease, combined with continued consumption by biota and oxidation of kerogen, which is organic carbon in sedimentary rocks, leads to a gradual decline in the atmospheric oxygen until it reaches zero within a few million years. Researchers estimate that plants that use the C3 photosynthesis process to fix atmospheric carbon dioxide should disappear in 600 million years, and C4 plants in 840 million years at the latest, due to the loss of carbon dioxide from the atmosphere. This massive disappearance of plants would have devastating consequences for all living beings as we know them today. Plants are at the very base of the food chain, providing food and energy for herbivores. Their decline means fewer food resources for herbivores, which in turn suffer adverse consequences. Their populations begin to decline, upsetting the balance of ecosystems. Without plants to produce oxygen through photosynthesis, animals would face a disastrous situation. Large endothermic animals, such as mammals and birds, would probably be the first to disappear, due to their higher oxygen requirements, compared to smaller endothermic and ectothermic animals. As atmospheric oxygen levels fall and temperatures rise, placental mammals will become particularly vulnerable. Not only do they have higher oxygen requirements than non-placental mammals, but embryonic development is also highly sensitive to excessive heat. Large herbivorous mammals would suffer from diminishing food resources as plant availability declines. Small mammals would be slightly less affected due to their lower oxygen requirements and surface-to-volume ratio, which facilitates heat dissipation. Placental mammals experience higher body temperatures than marsupials and monotremes, making them potentially more sensitive to rising temperatures. Birds may be better adapted to survival than larger mammals, as their generally smaller size means they need less oxygen. What's more, migratory birds in particular would be better equipped than animals of a similar size, thanks to their ability to travel long distances in search of cooler refuges. Nevertheless, the number of such refuges would decrease as temperatures continue to rise. These refuges would also be likely to be found at higher altitudes, where less land surface would be available, limiting population size as species migrate to higher altitudes. Ectothermic vertebrates such as fish, amphibians, and reptiles could survive longer than endothermic animals in this scenario, thanks to their better heat tolerance and generally lower oxygen requirements. However, reduced water availability would make some amphibian species more vulnerable in such an environment. Fish species would also be at risk, although rapid evaporation from the oceans would not occur at this stage. Marine species may have a better survival capacity than freshwater species due to the greater volume of ocean water compared with freshwater. For ectotherms, ambient temperature influences their metabolic rate. An increase in ambient temperature would lead to an increase in metabolic rate, and therefore a greater need for food. As a result, surviving species could be exposed to starvation. Reptile species whose sex determination depends on temperatures would be more sensitive to rising temperatures. Invertebrates could be the last animals on Earth before all animal species disappear. Some insects, such as beetles, can survive temperatures of up to 56 degrees Celsius, or 133 degrees Fahrenheit. In general, terrestrial life would initially be more vulnerable than marine life, due to the regulating effects of water temperature. However, the loss of terrestrial vegetation would lead to a reduction in nutrients reaching the oceans. Isolated communities in marine ecosystems, such as animal populations living near volcanic vents, would probably survive longer. Depending on the half-life of oxygen in the atmosphere, animal life could persist for up to 100 million years after the disappearance of plants. Some cyanobacteria and phytoplankton could survive without plants, as they are able to tolerate carbon dioxide levels as low as 1 part per million. They could persist until the atmosphere becomes too depleted of carbon dioxide to allow any form of photosynthesis. In one study, researchers claimed that a specific form of animal life could persist even after most plant life on Earth had disappeared. They used fossil evidence from the Burgess Shale in British Columbia, Canada, to study the climate of the Cambrian explosion, and used it to predict the future climate when global temperatures would rise due to a warming sun and decreasing oxygen levels, leading to the ultimate extinction of animal life. Initially, they expected some insects, lizards, birds, and small mammals to persist, as well as marine life. However, without a continuous supply of oxygen from plant life, they estimated that animals would probably die of asphyxiation. Even if enough oxygen were to remain in the atmosphere, thanks to the persistence of some form of photosynthesis, steadily rising global temperatures would lead to a progressive loss of biodiversity. As temperatures continue to rise, the last animals will be forced to move to the polar regions, or even underground. They would mainly be active during polar night periods, and would go into aestivation during polar day periods due to the intense heat. Much of the Earth's surface would become an arid desert, and life would concentrate mainly in the oceans. However, due to a decrease in the input of organic matter from the land and a reduction in dissolved oxygen, marine life would also disappear, following a similar pattern to that of the land surface. This process would begin with the loss of freshwater species and end with the invertebrates, particularly those not dependent on living plants, such as termites, or those found near hydrothermal springs, such as worms of the Riftia genus. Without CO2, photosynthesis can no longer take place. Without plant life to recycle oxygen back into the atmosphere, free oxygen and the ozone layer will disappear from the atmosphere, allowing intense levels of deadly UV light to reach the surface. As a result of these processes, multicellular life forms could become extinct in around 800 million years, and eukaryotes in 1.3 billion years, leaving only prokaryotes. To meet the Sun's energy needs, the nuclear fusion reactions taking place at its core convert around 500 tons of hydrogen into helium every second, The main effect of this alchemy is a progressive reduction in the number of particles energy the sun releases. This is why the sun's luminosity increases with the passage of time. Thanks to an effective greenhouse effect, the Earth has maintained a stable temperature, apart from a few periods of glaciation, which have enabled life to evolve on its surface. For hundreds of millions of years, the Earth has not undergone any significant change in its ocean mass, thanks to the near equilibrium of mantle water inflows and outflows. To maintain water in a liquid state on our planet, it is essential to establish a balance between the solar energy absorbed and that emitted, enabling us to maintain adequate temperatures. This balance is crucial to the survival of life as we know it. When the amount of greenhouse gases in the Earth's atmosphere increases, as is currently the case, a new energy balance is created, where the greenhouse effect creates an additional blanket, causing the surface to warm up. The Earth has an integrated regulating mechanism called the carbonate-silicate cycle, which controls the amount of carbon dioxide in the atmosphere to maintain a stable climate. Unfortunately, this cycle operates on a timescale of the order of 1 million years, making it too slow to be an effective solution for the current global warming problem we humans face. Progressively, even during the current calm period of hydrogen combustion, the Sun is inexorably rising in temperature. Some 4.5 billion years ago, at the very beginning, its luminosity was equivalent to 70% of today's level. By the time of the Great Oxygen Event some 2.4 billion years ago, its brightness had already reached 85% of today's level. For the next billion years, the Sun will continue to produce nuclear energy by converting hydrogen into helium. This is what almost all stars do most of the time. As the Sun converts hydrogen to helium in its core, the average molecular weight increases, leading to a rise in core temperature and the speed of the fusion reaction, known as the proton-proton chain. This gradually leads to an increase in the star's energy release. As a result, the Sun will shine even brighter. When the amount of incoming energy increases, it can also contribute to global warming. This is precisely what happens when the Sun's brightness gradually increases. Although the Earth's climate may experience shorter-term variations due to the seasons, changes in atmospheric composition, such as the addition of man-made greenhouse gases, as well as factors such as volcanic dust and Milankovitch cycles, the Earth's surface is experiencing a slow but steady warming due to increasing solar luminosity. Over a period of time, perhaps even several 100 million years, the Earth's feedback may attenuate this effect. The greater the thermal energy, the more intense the evaporation, hence the increase in cloud cover, which contributes to the reflection of most sunlight back into space. Increased thermal energy means faster weathering of rocks, greater absorption of carbon dioxide, and lower levels of greenhouse gases. Thus, negative feedbacks will preserve life-supporting conditions on Earth long enough. At some point, the Earth's atmosphere will reach a threshold where it will no longer be able to maintain a stable energy balance, leading to an amplification of the greenhouse effect. This phenomenon is often likened to a runaway greenhouse, characterized by positive feedback. As the planet's surface warms up, water evaporation from the atmosphere increases. Water is a powerful greenhouse gas, which reinforces the greenhouse effect and further warms the planet's surface. For several million years, cellular life can persist in such conditions. However, the critical moment will inevitably arrive when the greenhouse effect becomes uncontrollable, warming the Earth's surface to the point where the oceans reach a state of complete evaporation. Despite the increased amount of water vapor near the Earth's surface, there will be no liquid ocean left. After that, it will only take a few 100 million years for the oceans to evaporate, transforming the atmosphere into an endless pool of steam. When ultraviolet light interacts with atmospheric gas, it can cause the gas to heat up further, meaning that more heat is transferred to atmospheric water when it interacts with extreme ultraviolet light. As a result, the water absorbs more energy and heats up faster. This leads to an increase in water evaporation, and consequently, a more rapid loss of water from the Earth's surface. Another way of explaining this is to use the concept of the habitable zone, which refers to the orbital region around a star where a planet can maintain liquid water, provided it has a suitable atmosphere. At present, the inner edge of the Sun's habitable zone is around 95% of the distance between the Earth and the Sun. Our planet will then be completely devoid of life, but the real apocalypse will come later. As the Sun's luminosity increases, the inner edge of the habitable zone will move progressively further out. It's hard to say exactly when the inner edge of the habitable zone will reach the Earth's orbit, but it's estimated to be around 1 billion years. Some extremophiles may still live in refuges at higher latitudes or deep underground, but these will only be ephemeral remnants of a once exuberant biosphere, a situation that could recall the attractive symmetry of life's beginnings on Earth. In all likelihood, Earth will follow the fate of Venus, becoming a hot, barren world. As the habitable zone of our Sun has shifted towards the outer solar system, Mars is now located in this zone. It is possible that Mars's surface temperature will gradually rise. Carbon dioxide and water currently frozen beneath the Martian soil will be released into the atmosphere, creating a greenhouse effect. This will warm the planet until it reaches conditions comparable to those on Earth today, potentially offering a new island for life. According to computer models, the Moon's presence seems to stabilize the Earth's obliquity, helping to avoid dramatic climate changes. This stability is due to the fact that the Moon accelerates the precessional motion of the Earth's rotational axis, preventing resonances between the precession of the rotation and the precession of the planet's orbital plane. The tidal acceleration caused by the Moon slows the Earth's rotation and increases the distance between the Earth and the Moon. As the semi-major axis of the Moon's orbit continues to increase, this stabilizing effect will diminish. At some point, the disturbances will probably lead to chaotic variations in the Earth's obliquity, and the tilt axis could tilt to angles as high as 90 degrees to the plane of the orbit. This is estimated to happen between 1.5 and 4.5 billion years ago. High obliquity would probably lead to dramatic climate changes and could compromise the planet's habitability. When the Earth's axial tilt exceeds 54 degrees, annual insolation at the equator becomes lower than at the poles. It is possible for the planet to maintain an obliquity of 60 degrees to 90 degrees for periods as long as 10 million years. The likely consequence is that ocean evaporation, plate tectonics, and the entire carbon cycle will come to an end. This could happen in around 2 to 3 billion years' time, when the planet's magnetic dynamo could cease to function, leading to the decomposition of the magnetosphere. This would lead to an accelerated loss of volatile elements from the outer atmosphere. In 2.8 billion years, the Earth's surface temperature, even at the poles, averages 147 degrees Celsius, or 297 degrees Fahrenheit. Life is reduced to single-cell colonies in isolated and scattered microenvironments, such as underground caves, and dies out everywhere else. Every second, the sun emits a solar wind in the direction of our planet, corresponding to a flow of 1 million tons of protons and electrons. These particles are stopped in their tracks by the Van Allen belts, the Earth's magnetic field. Stretching over 70,000 kilometers or 43,000 miles, it originates from the Earth's iron-nickel core. The core is composed of a solid part, the seed, and a liquid layer 2,000 kilometers or 1,240 miles thick. The uninterrupted stirring of the liquid metal layer leads to the formation of the magnetic field. At present, the radius of the inner core is increasing at an average rate of around 0.5 millimeters per year, at the expense of the outer core. Virtually all the energy required to power the dynamo is supplied by the inner core. Within 3 billion years, the inner core is expected to absorb most, if not all, of the outer core, resulting in an almost entirely solidified core, composed mainly of iron and other heavy elements. The remaining liquid envelope will consist mainly of lighter elements that will undergo less mixing. Tectonic plate dynamics are generated by the transfer of heat from the Earth's core to the surface. This heat transfer takes place through the mantle by convection, sometimes combined with thermal conduction. When heat plumes reach the crust, they reach their heat and are pushed out by new hot plumes. This horizontal movement in the upper mantle is the driving force behind the movement of tectonic plates. However, as the Earth cools over time, the liquid outer core gradually solidifies. This solidification reduces convection in the mantle, limiting the power available to move the plates. Eventually, after around 3 billion years, convection will cease completely, putting an end to tectonic plate movements. If plate tectonics cease at some point, the Earth's interior will cool less efficiently, slowing or even halting the growth of the inner core. In both cases, this could lead to the loss of the magnetic dynamo. Without a functional dynamo, the Earth's magnetic field will weaken rapidly over a geologically short period of around 10,000 years. The disappearance of the magnetosphere will lead to increased erosion of light elements, notably hydrogen, from the Earth's atmosphere into space, creating conditions less conducive to life. In around 4 billion years, the increase in temperature at the Earth's surface will trigger an uncontrollable greenhouse effect, creating conditions even more extreme than those on Venus today. This will heat up the atmosphere and raise the surface temperature above 500 degrees Celsius or 932 degrees Fahrenheit, high enough to melt the planet's surface in some places. Nevertheless, much of the atmosphere will be retained until the Sun enters its red giant phase. At that point, the Earth's biosignatures will disappear, to be replaced by signatures caused by non-biological processes. From then on, all traces of Earth's life history will be completely erased. In 4.5 billion years, interactions between the Andromeda Galaxy M31 and the Milky Way will form a new galaxy called Milkomeda. The Andromeda Galaxy, also known as M31, is a spiral galaxy containing up to 1,000 billion stars, compared with 300 to 400 billion for the Milky Way. Made up of gas and dust, it adopts a flattened disk shape and contains a bulge at its center. Originally located 2.55 million light-years away, the Andromeda Galaxy has always been the closest to the Milky Way. It has been gradually closing in on the Milky Way at a speed of 120 kilometers per second, or 75 miles per hour. At first, the two galaxies don't seem to have collided. Being so far apart, the stars will initially pass each other without colliding head-on, before moving apart. Sometime later, this apparent choreography leads to a new rapprochement, this time followed by a strong interaction between the two galaxies. Their orbits are strongly affected by the anarchy of gravitational forces in place during the galaxy's interpenetration. The result, after 2 billion years, is the birth of a gigantic system with little interstellar gas, a new galaxy, Milkomeda. Unlike its two parents, this new galaxy is elliptical in shape, and the stars it contains are scattered around a sphere. The Milky Way and M31 no longer exist. This collision will not disrupt the orbits of planets within the solar system. While the gravity of passing stars can detach planets in interstellar space, the distances between stars are so great that the probability of the Milky Way-Andromeda collision causing disruption to a given star system is negligible. Although the solar system as a whole could be affected by these events, the Sun and planets are unlikely to be disturbed. The new galaxy sees a new outburst of stars, but as the little remaining gas is rapidly consumed, star formation comes to a halt, and the new galaxy will slowly fade away as its new stars die out. In 5 billion years' time, the Sun will leave its main sequence and begin its transformation into a red giant, having exhausted the hydrogen reserves in its core. The energy released during the fusion of hydrogen nuclei in the Sun's core fuels the frenetic agitation of lively particles that exert a powerful outward pressure. It is thanks to this pressure that the Sun swells and does not collapse under its own weight. Until now, this balance has been maintained, but now at 5 billion years, this is no longer the case. Although the Sun still abounds in hydrogen nuclei, there are virtually none left in its core. Hydrogen fusion produces helium, whose nuclei are heavier and denser than those of hydrogen. It is in the core of the Sun that the temperature is highest, at around 15 million degrees Celsius, or 27 million degrees Fahrenheit. The fusion of hydrogen into helium requires 10 million degrees Celsius, or 18 million degrees Fahrenheit. On the other hand, helium fusion requires a temperature of the order of 100 million degrees Celsius, or 180 million degrees Fahrenheit. The Sun is nowhere near this threshold, so as helium replaces hydrogen in the core, the fuel supply for fusion will diminish. Pressure from energy production will decline, and gravity will prevail, causing the Sun to implode. As its gigantic mass collapses in on itself, the Sun's temperature will rise dramatically. Despite this pressure and extreme temperature, helium fusion is still not possible, and the hydrogen then triggers a second phase of fusion within a thin layer around the helium core. As hydrogen fusion proceeds at an inordinate rate, the thrust is much more intense than before. The Sun swells to colossal proportions, reaching over 100 million kilometers, or 62 million miles in diameter, almost 100 times its current diameter. Transforming into a pulsating red giant, it will become thousands of times brighter than it is today. It leaves its main sequence to become a red giant. Naturally, the planets in the solar system will be directly affected by this change. The Sun, with its diminished mass, exerts less gravitational attraction, enabling the planets to migrate to more distant orbits. But do the planets go far enough to win the race against the Sun's increasing diameter? Mercury loses the race, swallowed by the Sun and briefly vaporized. Mars, orbiting further out, escapes unscathed. Venus is lucky. The Sun stops swelling just before it reaches its new orbit, and at the same time, the Earth is also spared. Nevertheless, conditions are fundamentally different. Earth and Mars rotate synchronously with the Sun. The average temperature is now several thousand degrees. What does a sunrise look like from Earth today? Instead of a warm, cheerful yellow disk, a gigantic red circle slowly settles above the horizon. It won't be long before Mars suffers the same fate as Earth. The atmosphere begins to warm. Potential life forms on this planet won't survive another 1 billion years. 2 new orbits are now taking their place in our solar system's habitable zone, the orbits of Jupiter and Saturn. Although neither planet is conducive to life, either Jupiter with water in its clouds or Saturn made up entirely of gas, their respective moons could become suitable places for the appearance of primitive life once their temperatures have risen. In this way, simple organisms could see life on the surface of Saturn's moons, Enceladus or Titan, or Jupiter's moon, Europa. Most of the Earth's atmosphere will gradually be lost to space. The Earth's surface will be transformed into an ocean of lava, with floating continents of metals and metal oxides and icebergs of refractory materials. Surface temperatures will rise dramatically, exceeding 2,000 degrees Celsius or 3,632 degrees Fahrenheit. Then, over 12 billion years old, the Sun's most rapid expansion phase as a red giant will occur in its final stages in 7.4 billion years' time. At this stage, it is likely to expand sufficiently to reach a maximum radius of around 1.2 astronomical units. The Sun will have lost more than a third of its current mass, which will have dispersed in the form of an intense solar wind. This loss of mass will cause the orbits of each planet to expand considerably. Considering only this phenomenon, Venus and Earth could probably escape incineration, but other studies suggest that the two planets would still be absorbed due to tidal interactions with the tenuous gas of the Sun's expanded outer envelope. Forecasts for the end of our planet are therefore rather gloomy. The Earth's gravitational interaction with the Sun's outer atmosphere will cause the Earth's orbit to shrink. The drag effect of the Sun's chromosphere will progressively reduce the Earth's orbit. These effects will partly compensate for the Sun's loss of mass, making it likely that the Sun will eventually engulf the Earth in around 7.59 billion years. The Sun's atmospheric drag can also cause the Moon's orbit to disintegrate. As the Moon's orbit approaches a distance of 18,470 kilometers, or 11,477 miles, it will cross the Earth's Roche limit, meaning that tidal forces exerted by the Earth will break the Moon apart, transforming it into a system of rings. Most of these orbital rings will begin to decay, and the residual debris will impact the Earth. As a result, even if the Sun doesn't directly engulf the Earth, it's possible that the planet will be left without a moon. But the Earth's decaying trajectory towards the Sun may eliminate the Earth's mantle, leaving only its core. Eventually, the Earth's core would also be destroyed 200 years later. According to this gloomy scenario, the Sun's red giant will simply destroy the Earth, which will evaporate into the hot solar atmosphere and cease to exist. But the story of the Sun as a red giant doesn't end there. As the hydrogen nuclei continue to fuse around the core, more helium will flow into the center, and the temperature will rise even higher. The cycle is fueled. Hydrogen fusion in the shell around the core accelerates, and the helium deluge at the center intensifies. This phase will last 500 million years before the core finally reaches the temperature required for helium fusion, a process that produces carbon and oxygen. This transition from hydrogen to helium fusion is marked by a spectacular eruption, during which the Sun contracts to a more constant subgiant structure. This new equilibrium was short-lived. 100 million years later, in the same way that helium had displaced hydrogen, carbon and oxygen nuclei drove helium out of the core and into neighboring layers. The combustion of oxygen and carbon now requires higher temperatures, at least 600 million degrees Celsius. This time, the core will never reach the temperature required to restart nuclear reactions. Its mass is not high enough to reach the temperatures required to fuse carbon and hydrogen nuclei into heavier, more complex elements. The helium shell continues to burn, and the core continues to contract until Pauli's exclusion principle stops the implosion. This quantum mechanism acts as a repulsion. It's as if the electrons refuse to be compressed any further, bringing the Sun's contraction to an end. The outer layers continue to expand and cool before being scattered across the cosmos. All that remains is a staggeringly dense ball of carbon and oxygen, known as a white dwarf. It will continue to glow for another few billion years. Fusion reactions will cease, and the temperature is no longer high enough. The sun's thermal energy will be gently dissipated into space, leaving a dark, cold globe. In 9 billion years, the sun, with a mass equal to 54% of its current mass, will become a white dwarf, composed of carbon and oxygen. Our sun is now dead, and its core laid bare. Its power of attraction on orbiting bodies such as planets, comets, and asteroids will have weakened due to its loss of mass in the previous stages. All the orbits of the remaining planets will expand. If the Earth is still around, its orbit is now twice as far away as the orbit we know today. All the planets will become dark, icy, and completely devoid of any form of life. They will continue to orbit their star, their speed reduced by the increased distance from the sun and its reduced gravity. More than 4 billion years later, the white dwarf sun has cooled to a temperature of 2,000 degrees Celsius, or 3,632 degrees Fahrenheit. Its luminosity falls below that of the sun. Its luminosity falls below 3 billionths of its current level. Its heat is no longer measurable. It is now invisible to the human eye. So weak is its radiation that it is drowned in that of the cosmic microwave background. The sun is gradually changing from a white dwarf to a black dwarf. The prospects for the destruction of our planet are not merely speculative, but based on solid predictions based on our scientific advances. Although we have knowledge of the Earth's distant future, it is up to us to shape the short-term future. This perspective raises fundamental questions about the future of life on Earth and our responsibility as a species to be aware of this potential future. It is crucial that we deepen our scientific knowledge, develop environmental preservation strategies, and explore innovative solutions to prepare our planet's biodiversity and sustainability. While this may seem a long way off on a human scale, it remains an inescapable reality in the natural evolution of our solar system. Understanding these phenomena and their implications enables us to better appreciate the importance of preserving our environment and exploring new avenues to ensure a sustainable future for generations to come. This is the ultimate dream of a scientifically literate society, and our only hope of staving off, as far as possible, the imminent threat of human extinction.